Salam, peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Remember the language we are learning together. There is one field, phi, the holophase, the single cyclic movement from which all reality unfolds. When phi differentiates, that one movement generates its first derivatives, and with them, the three dimensions appear at once: time as omega, space as k, and motion as v. From that first differentiation upward, every higher derivative is an echo of the one below it, an infinite ascent of finer and finer reflections of phi's original movement. And because the dimensions are born from that first echo, time, space, and motion also reverberate into infinity, carrying phi's unfolding into ever deeper rhythms, structures, and flows. Thus, the entire universe, every law, every pattern, every force, every particle, every phenomenon, is nothing but phi, endlessly echoing through its derivatives and their dimensional shadows. All of existence is the infinite echo of one field. Today, we listen to just one of those echoes. In our last exploration, we completed the second-order spatial nuance block. We met shear and twist, the sliding and spinning of patterns. And we saw that space does not just bend and gather, but also rubs and rotates. The spatial tower stopped feeling like a rigid, static grid and began to feel like a living, flexible fabric, capable of being stretched, folded, twisted, and sheared. Now we take a profound step. We leave the pure towers, the temporal tower of omega and alpha, and the spatial tower of k, a, curvature, convergence, shear, and twist. We step onto the bridge between them. We enter the realm of mixed derivatives, where time and space are no longer separate questions, but intertwined conversations. Here, how time changes depends on where you are, and how space changes depends on when you look. Today, we meet the letters that capture this intimate dance, the mixed second derivatives. We witness time and space refusing to stay in their separate towers, and instead weaving together into a single, richer fabric. Let us begin with a clear picture in your mind. Imagine you stand on a cliff, watching waves rolling in from deep water. Far out at sea, the waves are long, smooth swells. They have a certain spatial pattern, which we encode as K, and a certain temporal rhythm, which we encode as omega. At first, you can imagine adjusting these seemingly independently. You might change how close the crests are without changing how quickly they pass, or change the rate at which they pass without changing their spacing. But now, watch carefully as those waves move into shallower water near the shore. Suddenly, the story changes. The waves slow down, so their temporal rhythm changes. Omega decreases. At the same time, their crests bunch together, their wavelength shortens, so the spatial pattern, K, changes as well. And these two changes are linked. The slowing causes the shortening feeds back into the slowing. Time change affects space change, and space change affects time change. This coupling is what mixed derivatives capture when we speak the holophase language. They are phi's way of expressing that time and space are not separate dials, but coupled aspects of one unfolding. You can think of this as asking two intertwined questions about phi instead of just one. The first is, how does the spatial pattern change as time passes? That is, the space change of time change. The second is, how does the temporal rhythm change as you move through space? That is the time change of space change. These are mixed questions. They do not ask only about time or only about space. They ask how time and space talk to each other. This mixing is everywhere in our universe. It appears in the Doppler effect, when the pitch of a siren changes as it moves toward you and then away from you. It appears in dispersion, when a short pulse of light spreads out as it travels through glass. It appears when weather systems evolve while they drift across oceans and continents. Whenever local change is tied to transport, whenever here and now is linked to there and then, mixed derivatives are silently at work. In the Holophase language, we have been building a kind of grammar. Pure temporal derivatives like omega and alpha serve as the nouns and adverbs of time. Pure spatial derivatives like k, a, and curvature play the role of nouns and adjectives of space. Mixed derivatives are different. They are like conjunctions that join temporal and spatial clauses into a single sentence. Imagine constructing a space-time sentence. You might say, the pattern oscillates quickly here. That is omega and k, each giving you local information. You might say, the pattern oscillates more and more quickly. That brings in alpha, bending the rhythm of time. You might say, the pattern's oscillations become finer toward the center. That introduces A, bending the texture of space. But when you say, where the pattern oscillates faster, the spatial texture also becomes finer, you are not just modifying, you are relating. You are expressing a rule that links omega and k together. That is the voice of a mixed derivative. Mixed derivatives are relational operators between dimensions. They say, if time behaves like this here, then space must behave like that there. They encode the grammar of space-time coupling. In the master tree, this gives them a special position. They form the first explicit bridge layer between the temporal tower and the spatial tower. They are not purely temporal, not purely spatial, but truly space-time letters. Now let us translate this into operations a scientist could perform. Operationally, a mixed derivative measures how change in one dimension affects the rate of change in another dimension. Take something simple, the temperature in a room. Suppose it is warmer near a heater and cooler farther away. That is a spatial variation, a gradient, analogous to a K-field. Now turn on the heater and watch the room warm up. At each point, temperature begins to rise over time. That is a temporal change, like an omega-type behavior. A mixed derivative answers questions such as, how does the rate of warming depend on where you stand? Or, how does the temperature gradient itself change as time passes? These are two ways of describing the same thing, the time derivative of a spatial gradient or the space derivative of a temporal rate. In ordinary calculus, that is exactly what a mixed second derivative is. You differentiate once in time and once in space. For phi, these become questions like, how does omega vary across space? And how does k evolve in time? In real physical systems, these mixed derivatives are at the heart of wave propagation, diffusion, transport, and advection. They describe how a disturbance at one point in spacetime influences the future of neighboring points. They are about information flow. If you write down a heat equation that says the rate of temperature change in time depends on the curvature of temperature in space, you are already using mixed derivatives. If you write a wave equation that says the second time derivative of a field is proportional to its second space derivative, you are using mixed derivatives. If you add motion, such as a fluid carrying heat along, you introduce convective terms that multiply velocity by spatial gradients. That is mixed derivative structure again. Mixed derivatives are the way phi encodes that change here now produces ripples of change there later. Because every letter in this language must echo through time, space, and motion. Let us see how mixed derivatives express themselves across all three. In time, mixed derivatives appear as the rates at which propagation patterns themselves evolve, not just oscillate. They are what turn a local vibration into a traveling wave. Think of the sound of a moving ambulance. The siren at the source has a fairly constant frequency. But because the source is moving relative to you, the stationary listener, the frequency you hear depends on where the ambulance is and how fast it is moving. The pitch you hear rises as it approaches and falls as it recedes. The way perceived frequency changes in time at your position as the ambulance moves through space is a mixed derivative story. Omega is a function of both time and position. In heat diffusion, mixed derivatives determine how quickly the warming front moves through a metal rod. They tell you how long it takes for a change at one end to be felt at the other. In time, mixed derivatives turn something is changing here into that change is now spreading with a certain speed and shape. In space, mixed derivatives appear as maps of how temporal behavior varies across different locations. They create landscapes where time seems to have different styles of flow depending on where you are. Think about Earth's weather. The rotation of the planet shapes the way winds curve and storms spin, but the effect is different at different latitudes. Near the equator, the patterns are different from those at mid-latitudes or near the poles. The temporal dynamics of swirling systems depend on spatial position. That dependence is a mixed derivative phenomenon. Or imagine an orchestra playing in a concert hall. The same piece is played by all the instruments, but the sound takes longer to reach the back of the hall than the front. Different seats receive the same temporal pattern shifted in time. Arrival time depends on distance. That spatial pattern of delays, those little differences in when you hear each sound, is a mixed derivative field written in acoustics. Spatially, mixed derivatives tell you where rhythms are advanced or delayed, where oscillations line up or fall out of step, where phase differences build up over distance. In motion, mixed derivatives reveal themselves as the shape of propagation itself. Any realistic wave equation connects time derivatives and space derivatives so that disturbances move with finite speeds. In dispersive systems, where different frequencies travel at different speeds, the dispersion relation, the function that tells you omega is a function of k, is the central object. If you differentiate this relation, you get d omega over dk, the group velocity, which tells you how fast the wave packet moves. That derivative is quintessentially a mixed derivative. Its curvature, the second derivative of omega with respect to k, controls how pulses spread or compress as they move. In fluid dynamics, the material derivative, the derivative you experience if you move along with the fluid, combines a time derivative and a term that is velocity dotted with a spatial gradient. It embodies the idea that change experienced along a moving path is a mixture of local time change and moving through spatial gradients. Mixed derivatives turn motion from simple translation into rich evolution. They give us waves that distort, flows that mix, and signals that can carry structured information. Now let us locate mixed derivatives in the master tree. In Chapter 3, we have been exploring second-order semantics, the second questions we ask of phi. We asked the second question in time and discovered alpha, the bending of temporal rhythm. We asked second questions in space and discovered A, curvature, convergence, shear, and twist, the bending, gathering, sliding, and spinning of spatial texture. Mixed derivatives are second questions that mix dimensions, one derivative in time, one in space. They sit at the same height in the tree as alpha and curvature, but in a different column, the mixed column, between the temporal and spatial towers. Picture three vertical towers growing up from phi. One is the temporal tower, phi, then omega, then alpha, then higher temporal derivatives. One is the spatial tower, phi, then k, then a and curvature, and their higher companions. The third is the mixed tower, phi, then the first mixed derivatives, then higher mixed structures that involve more elaborate couplings of time and space derivatives. This mixed tower is where space-time becomes explicit in the language. It is where the language stops treating time and space as separate categories and begins treating them as different directions in one space-time fabric. Because mixed derivatives sit at these crossroads, they are deeply entangled with their neighbors. With omega and k, they are built directly from them. You take the space derivative of omega or the time derivative of k. With v, the motion letter, the relationship is even more central. Group velocity, the speed at which energy or information is transported by a wave packet, is essentially a mixed derivative, how omega changes with respect to k. With dispersion relations, mixed derivatives determine how different components of a signal spread out or stay together. With convection and advection, the main operator is a combination of time derivatives and velocity times spatial gradients, clearly mixing dimensions. With dφ, the total differential that already united time and space at first order, mixed derivatives ask how the different components of that total change, the time part and the space part, influence each other's evolution. Even causality and light cones are shaped by mixed derivatives. They determine finite signal speeds and the geometry of influence in spacetime. So, what is the deep semantic meaning of mixed derivatives? Pure derivatives tell you how something changes in one dimension. Mixed derivatives tell you how these changes are coordinated across dimensions. They say, time does not flow in isolation. How fast it seems to flow, how rhythms develop, depends on where you are in space. Space does not change in isolation. How its patterns emerge and shift depends on how time is unfolding. Mixed derivatives encode stories of spatiotemporal coherence. Waves propagating, signals carrying meaning, disturbances spreading out, patterns moving and changing shape as they move. Through mixed derivatives, the holophase language gains the ability to say not only this is the pattern and this is how it changes, but this is how that change travels and links distant points together. They are the letters that write sentences connecting here and now with there and later. They are the grammar of connectedness. Because this is a scientific language, mixed derivatives must be falsifiable. When mixed derivatives are zero, time and space changes decouple. You get idealized cases like perfect standing waves, where oscillations at each point do not transport energy along the medium, or static gradients that simply scale up and down uniformly over time. When mixed derivatives are constant, you get steady uniform propagation, plane waves in non-dispersive media traveling without distortion, or simple convection at constant velocity. But most natural systems have mixed derivatives that vary across frequency, position, and time. Waves in glass, sound in complex media, seismic waves in the Earth, all show dispersion where different components travel differently. Fluids with complex flows transport heat, mass, and vorticity in non-trivial ways. Shock waves and caustics appear when mixed derivatives become large or change rapidly. Mixed derivatives predict exactly how pulses spread, how wave packets travel, how signals distort. We can test these predictions. We can measure group velocity, dispersion, Doppler shifts, propagation speeds, and pulse evolution. If the relationships we observe cannot be expressed as mixed derivatives of phi, then we have found the limits of the holophase model. If they match, then we have evidence that the language is correctly describing reality's grammar. Once you know to look, you will see mixed derivatives everywhere. In light, you see them when a prism splits white light into colors, and those colors emerge at different angles and travel at slightly different speeds. In sound, you hear them when high-pitched sounds die away faster than low ones. In water, you see them when long swells and short ripples move differently across the surface. In fluids and weather, you see them in the transport of clouds, heat, and moisture by winds and currents. In quantum systems, you see them in the spreading of wave packets and tunneling behaviors. In gravity, you see them in the way gravitational waves travel at the speed of light, linking distant regions of spacetime through changing curvature. Now connect this to daily life. When you hear a siren's pitch change as a vehicle passes, you are experiencing mixed derivatives in your ears. When you watch lightning and then count seconds before hearing thunder, You are using a mixed derivative relationship between distance and time to estimate how far away the storm is. When you drop a bit of dye into water and then stir, you are turning simple spatial gradients into rich mixed derivative dynamics. When you watch traffic on a highway and see a wave of slowing cars propagate backward, even though all cars are trying to move forward, you are seeing a mixed derivative story in human motion. All of these are phi expressing its mixed spacetime echoes in familiar forms. And as always, we return to phi itself. Mixed derivatives are not new entities standing beside phi. They are just one more way phi can be asked questions about itself. First, we asked phi, how do you change in time? And we called the answer omega. Then we asked, how do you change in space? And we called the answer k. Now we ask, how do these answers talk to each other? And we get mixed derivatives. No new substance has been added, only new relations. It is phi saying, my temporal rhythm varies across space, and my spatial texture evolves in time. And these variations are coordinated. In this way, mixed derivatives complete the second-order semantic picture. We have pure temporal nuance, pure spatial nuance, and now the mixed nuance that stitches them into unity. Through all of it, there is still only one field, one cyclic movement, expressing itself in increasingly detailed ways. As we conclude our meeting with mixed derivatives, we also bring Chapter 3, Second-Order Semantics, to a close. We began with the whole language, seeing the master tree from phi up to infinite derivatives. We learned the first-order alphabet, phi, omega, k, d phi, and v. Then we stepped into second-order nuance, exploring alpha and the bending of time, A and the drifting of space, curvature and its focusing of patterns, convergence, shear, twist, and now the mixed derivatives that weave time and space into one story. We have discovered that time and space are not separate theaters, but intertwined stages of one play. Patterns do not simply sit in spacetime, they propagate through spacetime. The universe is not a static tapestry of events, but a dynamic fabric of connected becoming. Mixed derivatives are our first explicit glimpse of that connectedness in the language itself. They are where how things change becomes how changes travel and link distant points. In our next part, we will rise into Chapter 4, Higher Order Semantics. We will move beyond second derivatives into third, fourth, and higher orders. We will meet higher temporal derivatives like jerk and snap, higher spatial shape descriptors, and more refined mixed structures. We will see how the language can build infinite layers of nuance on top of the foundations we have now laid. But for now, hold this understanding. Time and space converse, they mix, they propagate together. The universe is not just textured in time and textured in space. Its time textures vary across space, and its space textures evolve in time. And these variations talk to each other through the beautiful, testable mathematics of mixed derivatives. Whenever you hear a siren's pitch change, whenever you watch waves spread and reshape, whenever you feel heat travel through a room, whenever you see information, rumors, or news spread through a community, you are witnessing mixed derivatives. You are watching phi's temporal and spatial echoes converse. You are reading the conjunctions that join space-time clauses. You are feeling, in your own experience, the intertwining of all things. Mixed derivatives are time-space intertwining, and this intertwining, as we will discover, is the beginning of waves, signals, causality, and the deep connectedness of our cosmos. Salam and peace be upon you until chapter 4.